the world's largest radio telescope is being built. It is actually an ancient land of Vajari Yamatji. The Aboriginal name is Inyari Manha Ilagari Bundura. I'm sorry, I might not be pronouncing it right. The traditional English name is the CSIRO Murchison Radio Astronomy Observatory, being built in Western Australia. But they're very keen to keep mentioning that this is being built in an ancient land belonging to the people who occupied or who were the earlier residents of Australia. So I thought it's very important for me to mention and share that information with you. Well, from the spotlight glittering Perth, I had to go to the outback of Australia, which is a very remote area. There are no airports in that area. So we were very lucky, being the Science and Engineering Advisory Committee. We had a special aircraft chartered for 3 of them, actually, for all the members of the SEAC, and we flew in a private aircraft. We went through Geraldton, in which they have a very sophisticated laboratory to test all the equipment that will go to the field later. It's because this is called AIV, Assembly, Integration, and Verification Testing. There is no need to worry about what testing that they are doing in this particular lab that I've shown you. It is a very highly enclosed lab in which no electronic signal goes out or nothing can come in. It is that kind of a lab to test all the equipment that goes to the Square Kilometre Array project. Well, we believe that deserts means it has nothing in it. But look at, the deserts are home to a variety of plants and animals that have adapted to survive in the harsh conditions. Well, we were a little bit late. We never got to see this much of flowers, but people told us that we were just a week late. But throughout Perth and wherever we went in the Western Australia, this really wild flower was always making its presence felt, and it was really an eye filler. It was really adventurous, very nice, and very happy to see this kind of flowering. These are all wildflowers. These are not gardens. You look at that. Look at that here, the extent to which the flowers have grown, and it's simply beautiful, and the variety is really mind-boggling. And then it's also not that. They have a lot of, small animals, but some of them are also they are, endangered species. And while building this telescope, as much as they take into account all the feelings and emotions of the Aborigines who are the real owners of this land, they also make sure that none of the local vegetation or the particularly endangered species are affected. They clear colonies, allow a buffer around them, and they go on to build the telescope. That's really a very, very important thing. They have an environmental advisor who is stationed all the time at the site. And I'll show you pictures of the site shortly. It's a really beautiful arrangement that they have made to make sure that as much of nature is left unaffected. Well, there is a very beautiful poem which I read, which is by Mary Oliver, which says, "Tell me, what else should I have done? Doesn't everything die at last and too soon? Tell me, what is it you plan to do with your one wild and precious life?" If somebody had asked this question to the astronomers in the world today would have answered, "We want to build the world's largest radio telescope." Friends, to the left, you're seeing a very small part, a sample of the world's largest telescope being built in Western Australia. Well, you will learn slowly that it is not one telescope. There are 2 telescopes, one in South Africa, one in Australia, and they have a headquarters in Manchester. So all these 3 telescopes, all these 3 institutions form one SKAO, Square Kilometre Array organization. So the idea of a Square Kilometre radio telescope emerged in 1996. So you see, look way back, 1996, 4 years before 2000, another 25 years, 30 years back. Scientists envisioned a telescope that could survey the sky 1,000 times faster than the existing instruments. And the major names which are heard, we should feel proud, is of Professor Govind Swarup from India, who built the two major radio telescopes that we see in India today. I will just show them later, but just remember that the idea of the entire square kilometer array was also a brainchild of Govind Swarup, Yuri Parizhsky in the USSR, Peter Wilkinson in UK, and Robert Brown, Gerdy Brown from Netherlands, and Peter Dwenny in Canada. And all these great scientists have contributed. Their teams have all been working all through to make their ideas into a real telescope. Well, it is very important to share with you the videos that the SKAO has made. I have been seeing these videos, but I found that no amount of words can really play or can substitute these. So I'll play a couple of videos of them during my talk at an appropriate place, because it's a talk on the square kilometer array. It is important to show you how the whole activity of installation began. See, 1996 was the seeding. That's when the idea seeded. There was a whole design phase. Now it has gone into the construction phase. And let us see what that is all about. Just give me a minute. I will have to stop share and share the video with you. Just give me a minute. I will do that. Stop share, screening, show captions. Where is the sharing? Oh my God. Share screen. All right. Share. You'll have to be a little bit patient with me when I change it. Yeah. Supriya, can you see that?
Yes, sir, we can see.
First, I'd like to say, welcome to our home here on Yamaji country.
Our nation is proud to be a founding member of the SKA Observatory. It is pleasing to say of those Australian-based businesses, Venture has been awarded contracts to begin the infrastructure construction with the support of the local Wadjuri small and medium enterprises. Not only will our astronomers get to use these incredible telescopes, but our businesses will benefit too. Developing cutting-edge technology for the SKA will expose Australian businesses to new skills and capabilities, making them more competitive.
We look forward to working with our Australian and international partners to achieve this vision with the support and to make the SKA telescopes a reality here in Australia and South Africa.
It's incredibly exciting. I've been involved in SKA for 10 years, was first proposed in the 1990s, so there are people who've been involved for a lot longer than I have. So it's amazing to be here on site, actually ready to start construction.
It's incredibly exciting to be here today, particularly on Wadjuri Yamaji country. It's a magical place. And today represents the culmination of nearly 25 years worth of planning and thinking about building one of the world's most powerful telescopes.
Well, that's why I like building telescopes. It's not to do the science myself, but it's to enable all the other scientists. So that's definitely part that I'm really excited about. And seeing the early science and then it's the science, that's the fun part for me.
As we prepare to turn the soil to mark the beginning of construction, we Wayiri acknowledge through ancestral bloodlines and knowledge of our connection to land is through actions, behaviours, story and custom. We invite the international community to connect with Wayiri in a meaningful way and work together.
It's understanding the dawn of the universe to the dawn of life in the universe. I think there's going to be some fundamental changes in our understanding of the universe around us.
The line that was used, and I can't remember who to credit, is it's not the beginning of the end, it's the end of the beginning. 2023 has really been a transition year for us. It's been going from this, we understand this instrument.
Yeah, that was the video that I just wanted to share and show it to you. Thank you very much. I hope you have got an idea of what it looks like, the land, the kind of the telescope that we are building in. That's only just a very beginning to give you a flavor of what is being built. Okay. Well, you must maybe asking the question, you're talking about the world's largest radio telescope, but many of you may not even have known that the optical telescope is different from a radio telescope. And therefore, let us spend some time exploring the frontiers of radio astronomy in as short a time as possible. I'll try my best to keep it short. Galileo used the telescope that he made in 1609 in Venice. It was almost 300 years or so until the 20th century. Astronomers learned virtually all they knew about the sky only from the radiation that is visible to the eye. That is what we call as the visible light. However, later astronomers discovered that there is radiation outside this visible spectrum also, and we have light coming from the ultraviolet, X-rays, infrared, and radio waves emitted by different celestial objects in the sky. It could be stars, it could be the medium between the stars, the galaxies themselves, the medium between the galaxies, etc. And there is a tremendous amount of importance of doing astronomy in various electromagnetic wavelength regions, because one object which is completely invisible at one wavelength can become clear and visible at another. So multi-wavelength astronomy is the basis of the modern astronomy in the 21st century. Well, if you ask the question, when was the first breakthrough happen coming out from the clutches of optical astronomy? It was in 1933 when an engineer called Karl Jansky at the Bell Telephone Laboratories, who was asked to investigate the origin of the hissing noise in the transatlantic telephone line, discovers that 20.5 megahertz radio waves are coming from the Milky Way or from the center of our galaxy. So that led to the real discovery of really going away from only optical astronomy. Today, all ground-based telescopes use what we call as atmospheric window. The atmospheric of the Earth allows optical waves, infrared waves, and radio waves to come through the Earth's atmosphere and reach the telescopes on the ground. Whereas when you want to look at the celestial objects at X-rays, gamma rays, or ultraviolet, you will have to take a telescope outside the Earth's atmosphere and make them space-based telescopes. So we are looking at telescopes today which do radio observations from the ground. The first person who built a telescope made for radio astronomy was Grote Reber in 1930. He built a 32 feet diameter telescope in 1937 in his backyard in Wheatston. He's considered the father of radio astronomy, even though it was Jansky who discovered that. It's because
Sir,
he was the first
your
to build a
screen
large...
is not shared, sir.
Oh, I see. I'm sorry. Thank you.
Okay. Yes, sir, visible.
Yeah, thank you. 1 second, slideshow. It's everything is clear now. At least it's working. Yeah, Reber, even though it was Jansky who discovered the radio waves coming from the celestial objects, it was Reber who is considered the father of radio astronomy because he built a radio telescope to map the sky. And he discovered many radio sources in the sky hitherto not known from the radio emissions. What are the benefits of observing in the radio? Why should we build radio telescopes? It's because it tracks physical processes with no signature at other wavelengths. See, man is a very, what you call a curious animal. He wants to understand the universe completely. But there are objects in the universe which only emit in radio, only in optical, some of them in X-rays. So he wants to build a telescope which would cover the entire electromagnetic wavelength regions. And radio waves can travel through dusty regions through which the optical waves cannot travel. It can provide information on magnetic field strength in the celestial objects. It can provide information on line of sight velocities of these objects and can tell us whether these objects are moving towards us or away from us. And also, radio astronomy can be carried out in the daytime also. So the most important point here is optical telescopes see only things like stars, whereas the radio telescopes see high energy electrons moving in magnetic field. And that's what we call as synchrotron emission. You see here, to the left, you see a picture taken with the optical telescope. To the right, you see an image taken with the radio telescope of the same region of the sky, but they're so different. So that is the most important point that I just want to bring about. Look at this another image, that this is what you see in optical, but when you go to the radio, you will see additional jets and the center of the galaxy, which corners a black hole. So what we see are entirely new processes of astrophysical phenomena like synchrotron emission, spectral lines coming from hydrogen atoms, which we have all studied in our PUC and BSc classes, discrete transitions in atoms and molecules, all start appearing very clearly and very beneficially in the radio wavelengths. That's why people built radio telescopes. Here is a further example. You see, the man has eyes to see the Milky Way, our own galaxy. In optical, it will look like this. But suppose the man had eyes to see them at 408 megahertz, it will look like this, completely different. You don't see these, what we call as the North Polar Spur, which are the remnants of explosions which took place millions of years ago, are not seen in the optical. So it is to see these different kinds of phenomena that man went from optical telescopes to radio and then to other telescopes. Look at this. This is a very powerful radio galaxy. There is a black hole at the center, and the jets of particles coming from it impinge on the intergalactic medium to provide the best known sources in the sky. That's a source called Cygnus A, and these sources are highly powerful. They give out radio power of the order of 10 to the power of 23 to 10 to the power of 28. But don't forget, even though they are so powerful, they are so distant in the universe. I'll show you some pictures of how distant they are. And the amount of radiation you receive from them here is very small, even though they are highly powerful radio sources. Radio astronomy not only led to different types of mechanisms and physics being learned, it also opened up several new sources. For example, they found a black hole at the center of a galaxy, which is sort of gobbling away all the matter around it, and it came to be known as a quasar. And the quasar was discovered by radio astronomy. This is a remnant of a massive star that exploded just 300 years ago, and that is known as Cassiopeia-A, a supernova remnant seen with a telescope in Very Large Array in America. And next, the pulsars, the very strong magnetic field and very heavy stars, which are only theorized, were discovered by radio astronomers. Actually, it was discovered by Jocelyn Bell and Anthony Hewish in 1967, and in 1968, Anthony Hewish won a Nobel Prize for this discovery. And it is such a very heavy star, unlike our sun. If you take a teaspoonful of this pulsar, which is a neutron star, it weighs about 10 million tons. My God, what an amount of massive material it must be. So the radio astronomy has been a birthplace for several new objects and new phenomena. And the most important thing is we all have heard about the expanding universe and the Big Bang theory. And the most supportive evidence for Big Bang theory came from the work of Penzias and Wilson, who discovered in 1978 the remnants of this Big Bang, which is called as the cosmic microwave background radiation. And they won the Nobel Prize for their work. And there have been several experiments which have been carried out post-1978 to study and understand this relic radiation of the Big Bang. And they have given very interesting results. Like, for example, one of the probe, which is called the Wilkinson anisotropy probe, has shown that the matter that we talk about, the atoms, electrons, and all the things, they form only 4% of the entire universe, and the remaining, they form only 4% of the universe, whereas the remaining is made up of dark matter and dark energy. That means the 96.96 to 95% of the entire universe is not known. We don't know what is dark matter. We don't know what is dark energy. And even though the radio astronomy has made a lot of strides, there are so many questions unanswered in this universe. So therefore, they started building telescopes which are bigger and bigger in size, because an optical wavelength is in microns, whereas when you hear let's say a very simple FM transmission coming at 100 megahertz, you all know about Mirchi and other stations which broadcast at 92.7 megahertz, 100 megahertz, which is 3 meters. So from micron to a meter, there is a size difference of about 1 million times. And therefore, from eye to a radio telescope, there will be a large size of the radio telescope required to see the same detail in the sky. That's why people started building larger and larger radio telescopes. See, this is what they built, a telescope, and this is a parabolic dish in which the incoming radiation is all brought to focus, because the distances that the light travels from a plane wave to the focus are all equal, and therefore they get focused at the focal point. And at the focal point, we keep a very sensitive radio receiver to measure the radio radiation which is coming. The radio telescopes that man built in the last several years come in 2 basic flavors, which are called single dish telescopes and very large arrays. I will come to in a minute why large arrays, but look at this dish, which is the single dish. And man built, in both the flavors, a large number of radio telescopes. For example, Govind Swarup built quite some time back, in 1976 or so, a dish which is 530 meter long and at a height of about 36 meter or so, which is equivalent of not a spherical lens, but a lens, a cylindrical lens, which we use for correcting our astigmatism. This is a radio lens which is exactly made out of a system which exactly works like a lens which corrects your astigmatism. And that is a frequency. Its operating frequency is about 327 megahertz. Please, if you go to Ooty, don't come back only seeing the honeymoon spots. This is a wonderful telescope. It has got an enormous amount of effort that has gone in India to build this telescope, and it's working even today. It's a 530-meter long radio telescope. And then we have a telescope which is 64 meter built in Australia. And this works in the frequency range 700 megahertz to 4 gigahertz. This was built way back in 1954 to 1960. So 1960, that means 40 plus 25. Still, this telescope is active, 65 years. Why I am saying this is very important when we come to the end of my talk. 65 years, the lifetime of a good radio telescope could be as large as 65, 70 years. This is an Effelsberg telescope in Germany, which is 100 meters. This is once again a green bank telescope, which is also 100 meter in United States of America. You saw the different radio telescopes operate in different frequency bands. Optical wavelengths cover only an octave in frequency, 0.4 to 0.8 microhertz. Whereas when you talk of a radio wavelength, it runs from millimeters, which is the microwaves that you use to heat in your home, to the so-called the FM station that you hear. They all have wavelengths of meters. Therefore, this is 3 orders of magnitude. Millimeter to meters, the wavelength changes by 3 orders of magnitude. So a single radio telescope will not work in the entire frequency range, just like you have a radio receiver for FM, then AM, then shortwave 1, shortwave 2. Just like that, we have radio telescopes which are operating in different frequency bands. And the bandwidth and the size of the telescope determines the sensitivity of the telescope. It's very, very important, sensitivity and resolution. There are 2 important aspects which depend upon the size of the dish and the amount of this bandwidth that we are taking in. It depends on both of them. Well, when people realize that they can't keep on building telescopes which are larger and larger, there was a scientist called Ryle in 1974, found out that, look, it's not necessary that you should build a large telescope, but you can think of a large radio telescope being made up of smaller antennas, and you can assemble a large number of smaller antennas and then make it work like a big radio telescope. That is what his discovery was. It is called aperture synthesis technique. And obviously, he was awarded a Nobel Prize for this work. And that is what is responsible for the second flavor of radio telescopes. This is, any one of you have seen the movie Contact will not miss out. This is the very famous array called Very Large Array in New Mexico, Socorro, which consists of, I'll come and tell you in a minute what it consists of. And this is an array. And here, the resolution depends upon the diameter D, whereas the resolution of this array depends upon this diameter D. And they track the sources in the sky for a large time and compensate for the amount that you don't have a filled telescope, which is 27 kilometers, whereas they track the source for a long time and compensate for the collecting area. That's what is called as interferometers in radio astronomy. Let's not go into more details of them, but you understand that there are single dishes and there are arrays. In an array, it is this distance which determines its resolution. Like, for example, the VLA that I showed you, that's a very large array in New Mexico, Socorro, consists of 27 25-meter antennas spread over a 36-kilometer baseline, and at a frequency of 75 megahertz, it has a resolution of about 24 arcseconds. When it goes to 45 gigahertz, it has a resolution of 0.043 arcseconds. The resolution of the eye is 60 arcseconds, which is about 1 minute. So look at that, what man has made with the work of Ryle. We have been able to build radio telescopes which are very large in size and which give the same resolution. Similarly, we have built our own telescope in our backyard called Giant Meter Wave Radio Telescope. Once again, this was built by Govind Swarup and his team by Tata Institute of Fundamental Research. Today, it is Yashwant Gupta, who is the director of the NCRA, who took us from GMRT to our participation in the SKA. I will come to it. The GMRT itself consists of a large number of dishes. It's located in Kodad, very close to Shirdi. And the GMRT consists of an array of 30 antennas, each of 45-meter diameter. And it covers a distance of about 25 kilometers. The GMRT has the largest collecting area among its peers. So Indians could be proud of having such a telescope. And that's what and then you can see its collecting area. I mean, it works in 4 bands, starting from 125 megahertz to 1500 megahertz. And it has a resolution of about 17 arc seconds at the highest at the longest wavelength to 2 arc seconds at 1.5 gigahertz. Beautiful. And its sensitivity is microjansky per beam. What is this microjansky, you may say? We don't understand that. Yes, just give me a minute. 1 Jansky is 10 to the power of minus 26 watts per meter squared per hertz. So little, 10 to the power of minus 26. If you look at the quiet sun, he has only 1000 Janskys. Whereas the value, the radio frequency interference from a telephone that you're using is 3 plus 3, 7, 11 into 10 to the power of 7 Janskys. So imagine the phone that you're using is 10 to a million times more strong or heavier radiation which your telephone is picking up compared to a weak source in the sky, which is a few Janskys. And the GMRT has been able to achieve sensitivities in the field of microjanskys. That is 10 to the power of a million times smaller than a microjansky. Then you may say, look, why are you guys so greedy? If you are able to reach such a sensitivity, why do you want to build the world's largest telescope? Are you not happy? The answer is here. NASA says very clearly that 96% of the universe is still undiscovered. The universe is about 13.7 billion years old. All the stars, planets, and galaxies that have been discovered make up only 4% of the universe, whereas the 96% is made up of dark energy and dark matter, and we still don't know anything about them. And then there is a very beautiful diagram which I want to share with you. Here is the 0 years of Big Bang to present age, which is 13.7 billion years. The first stars in the sky lit up when the universe was 1/6 of its current age. That means 400 million years after the Big Bang, the first stars were born. And believe me, no one has been able to see these first stars which are born in the universe yet. No telescope, neither GMRT nor VLA, has been able to reach the sensitivities required to look at these stars or their environments. And therefore, a large part of the sky still remains unexplored. So we have explored only 0.1% of the entire moving volume of the observable universe. So therefore, the world's radio astronomers have come together and said, hey, can we improve the resolution and can we improve the sensitivity? When Reber did his experiment to what the SKA wants to do, you see there is a 1, 2, 3, 4, 5, 6, 7, 10 to the power of 7 times improvement in sensitivity. A 10 million times more sensitive than the first radio telescope being built. And not only that, it's about the GMRT and VLA are still here. It's about 10, 100 times sensitive than VLA and GMRT. That is the ambition of the radio astronomers all over the world. Well, here is a beautiful picture, an artist's impression, also taking into account the artist's, the photographs of elements which have already been put in the two, South Africa and Australia. Here is a small picture of the two shown together, along with the Milky Way in the sky. Here is a beautiful painting of an Aborigine girl called Susan, who painted our home. It represents the beauty of the Aboriginal land with its rich red soil, wildflowers, and coming together of the entire community in Australia and all over the world to build this world's largest radio telescope. So I think it's a good time to see one more video. Just I'll stop sharing and I'll switch on to the next video. Just give me a minute. Well, then share screen. I'll have to share a different screen. Which one? This one. Where is the Firefox? Yeah, here it is. Share. Yeah, this is a very beautiful video telling us about why are we exploring this, building this telescope.
What did the universe look like when the first galaxies formed?
Come si formano i pianeti?
How many gravitational waves are passing through me right now?
And for me, the most important is there life out there?
We're building what will be the largest science facility ever built by mankind. What we're talking about is 2 telescopes.
These are going to spread out over literally hundreds of kilometers. It'll stretch out beyond the horizon. Our site's middle of the West Australian desert, far away from towns, radio interference. We're building hundreds of dishes in a remote location in the middle of South Africa. It's a hot environment, it's a dry environment. It's really tough.
Een project als dit kan alleen tot stand komen als wetenschappers wereldwijd met elkaar samenwerken.
We need astronomers to define the scope of the instrument.
We've got to get 500 engineers to work together over 20 countries in all the time zones in the world.
It's not building a jigsaw puzzle. The pieces keep changing.
Part A being designed in one place fits to part B being designed literally on the other side of the world. We've already started. We've got antennas at the site. There's equipment on the ground in South Africa and Australia. Imagine the amount of data that's flowing through the internet at any one moment. Huge amounts of data. That kind of level coming out steadily at about a terabyte of data per second.
We'll have a total of 100,000 kilometers of dedicated fiber within the observatory.
But the greatest computing burden is to take those data streams and to make sense of them.
Every year we'll be distributing up to 700 petabytes of data. There's this huge range of science we'll be tackling. There's the technology that needs to be developed to do that science.
Practically every subject of astrophysics can advance thanks to SKA.
That's from science to technology to societal benefits. This is what engages countries.
SKA is a project that will be used for 20, 30, 50 years. You want to be part of this fantastic adventure of the human mind.
Credo che siamo davvero alle porte del futuro. La scienza parla tutte le lingue del pianeta. Il suo linguaggio connette il mondo intero.
This signature is the real beginning.
I think people will look back and think this is the moment the SKA Observatory was created.
Just a minute. This is there when I left it. This is all over, this is over, this is over, this is over. Okay, fine. Yeah, we were here. Right. Sometimes you see that, sometimes you don't see. Okay. Yeah, fine. Somehow it has gone into that mode. All right. So you saw that the number of the scientific objectives of this telescope, which is too large, is unbelievable. From cosmology to cradle of life to the continuum sources beyond, gravitational waves, pulsars, and a variety of sources hitherto studied to a small detail. but it will be taken to its logical conclusion by these large telescopes. Then you can ask the question, all right, it's the world's largest telescope. Why are they built in such very remote locations in South Africa and Australia? Why not we build it close to some city or a place which can be easily accessed? Because radio telescopes, as I was trying to explain to you, are trying to observe very faint phenomena in the sky. And if they are not located far away from the human-made electronics and machines that emit very strong radio waves, it will interfere with the ability of the telescopes to detect faint radio signals. The reason why we have telescopes in South Africa and Australia is because those two have gone and developed very remote sites for the installation of these telescopes, and they have made it radio quiet zones. Just I will show you the picture. If you take a radio telescope and look at a frequency of about 100 megahertz and look at the flux density, the lines, look at the amount of noise from the man-made interference. If you go to Ooty, already there is a decrease. If you go to the remote Murchison Shire, then you hardly see only few bands which are noise, whereas the rest of that is in the remote Australian desert is almost noise-free. This is the reason why the telescopes like SKA are being built in very remote areas. Then you may ask the question, what makes SKA so special? In a short, it's a combination of smart design, cutting-edge technology, and the addition to the sheer scale of these telescopes, technology being brought by multiple regions in this entire Earth. That is, so many countries have come together to build it. And the SKA telescope, what does it consist of? If you say, why is it called a big data? You will find, let me just see whether it is, the amount of on-site processing that we need for processing the data that comes out of it will be by a supercomputer, which will be one of the top 5 fastest supercomputers in the world by 2022. Already we have passed it. So that is the kind of telescope that you are building, and that is the kind of, the computing power that you require to make images from these telescopes. Then only you can make translational science, new science, and can break the barriers which are holding us. Therefore, if you ask the question, will SK be a game changer? The answer is definitely yes, because you will find it is 135 times faster than a telescope called LOFAR in the Netherlands. It is 60 times faster than the VLA, the improved version of the Very Large Array in US. These figures set the scene for a number of fundamental discoveries which scientists are very eager to make and find out what lays in the deep remote corners of the universe. And why SKA is called a big data project, which I've already told you. In total, SKAO will archive 710 petabytes of data per year, and this would fill the data storage capacity of about 1.5 million typical laptops every year by today's standard. That is the kind of data that we are talking about, and it would require innovation in data processing, data mining, and imaging. All of them, there is a tremendous amount of scope for the scientists to innovate. So to make the story short, SKA-LO has 131,000 log periodic antennas. It has a collecting area of approximately 400,000 square meters. The distance to which the antennas are spread is 74 kilometers. It works in the frequency range 50 to 350. This is what is built in Australia, which is what I described. Let me not touch upon more of what is built in the mid, because that could be my next talk when they take us to South Africa and tell us about what they are building there. How much it costs? Well, SKA is a 2 billion euro project comprising a construction cost of 2 world-class telescopes, each of 1.3 billion for the SKA mid in South Africa, and 0.7 billion for the one in Australia. And this includes for the first 10 years of operations in 2020 to 2030, but we're already 5 years late from when we wrote down this. And where does the money come from? It comes from all the SKAO member states. Who is building this radio telescope will be the last video that I will show you and leave you at that. I think that I did not happen. Let me just see. Will give you a feel for how many countries are participating.
Having scientists in academia and industry working together has been key for us.
It's really important to cooperate with this big organization to improve the company, to improve the production.
We hope that over the next few years,
this is from India,
in collaboration with our international partners, we'll be able to build a powerful, very capable and robust monitoring and control system for their scale themselves.
My contract is to construct the frequency distribution system for the SK Mid telescope to ensure that all the antennas of the array are perfectly synchronized.
大家可以想象，它相当于6层楼高，一个天线现在40多吨，架起来这指向要这么高，然后我们这个天线在这么各种风力、温度和重力的条件下，它要保持不变形，所以这是很大的挑战。
Per migliorare le proprie conoscenze, le proprie tecnologie industriali, si è avvicinato ai Big Science Project. Uno di questi, il più importante, è SKA, sul quale stiamo sviluppando e realizzando i feed indexer.
We've been on a multi-decade journey. I am so excited to see construction starting in earnest and telescopes blossoming in the Karoo and in the Murchison in Western Australia.
Hosting the SKA-led telescope on Wajarri country here in Australia takes advantage of the unique radio quietness of our remote Midwest region. The challenges of the SKA project are an incredible opportunity for Australians to showcase our skills to the world across industry, government and tertiary sectors.
We've learned that these projects can have an impact in education and development of the countries. So the SKAO is going to bring more training in the STEM field.
This project is one of the major successes of South Africa broadly, but of science and technology in the country in general.
We want to do our bit to support the economy. We want to be good neighbours to all of the stakeholders.
We have data challenges, we have people challenges, we have technical mountains to climb, and the square kilometre array will do these on scales never before seen. This is going to unveil an invisible universe which we would never possibly have been able to see without it.
The SKA is going to have a huge impact on our understanding of the fundamental quantities of the universe, be able to inspire the next generation of astronomers to ask the next generation of questions.
We are sure that in the coming years we are going to live a great adventure together with our partners from countries all over the world. And we are proud and very excited to help making the SKA a reality.
So that's it. I mean, in a sense of the word, that doesn't matter. Then there are always questions how long the SKA will be operational once it is complete. Well, it will expect it to be operational for at least 50 years. And that's why the reason is in 2024, Indian cabinet approves 1,250 crores as India's contribution for the world's largest radio telescope project. And we are a part of this mega science project. And we can all be proud that scientists in Bangalore and Pune and many other places all over India are contributing to their best to what we can do to this world's largest telescope. Well, I'm really lucky to have been a part of the Science and Engineering Advisory Committee, and thank all the astronomers for having made me their representative. Here is my happy face writing my name on one of the antennas when I visited them in September. And thank you for patiently listening to my, I don't know what to call it as, a talk or a videos coming from SKA.The and all the slides. Thank you very much. Thanks a lot to having given me an opportunity to share this excitement.
Thank you, sir. Really, we are proud of you being in this project, sir. Really. It's a great opportunity to interact with you and to know more inside things about SKA. Now we can take questions. If any questions, you can unmute and ask. Yes, sir. Kagli, sir, go ahead.
Okay. Can you tell us what exactly are the technical responsibilities of the Indian team? What exactly you'll be doing, and what exactly are the privileges we get, by joining this project? Do we get all the data or whatever?
Yeah. But let me first answer the first question. There were two phases of this project, where there was a design phase when the National Center for Radio Astronomy Astrophysics, which was a part of the TIFR, that is NCRA in Pune, was the lead team for designing telescope manager. What is a telescope manager? Is like a central nervous system for the entire human being. It really takes information from such a large variety of instruments that are used to collect data and reports its health, report its data, and tells us whether things are running the way it should. Otherwise, it is impossible for a human to really look at 11,000 antennas and find out what has gone wrong where. So a telescope manager was conceived by the scientists and engineers of NCRA, more so by the industry, which really came up with a complete software design for the telescope manager. That was the first part. The second part, as you saw, it was only in January 2024 that this 1,250 crores has been sanctioned by the cabinet or the Indian government for us to join back after the design phase, when the installation of the operation phase. And we are trying to niche out or carve out very important areas of work in which we can concentrate. For example, the one that we are known for, the signal data processing, is one of the most important scientific/technical contributions that the scientists from India would be making. And what are the benefits? Well, the key science projects of looking at when the first stars were born, when the first galaxies were born, what is the environment which is called as the cosmic dawn, because that was when the stars or luminous objects in the sky were born. That is a key science project. And unless you are a member, you won't get data to analyze that and make discoveries. So we would be members in majority of the key science projects, and how the data will be shared is still an ongoing process. to be completely clear to everybody. But more than that, the need of the hour is for us to generate the required human resource. The telescope would be ready, if I just don't mind me showing this, by 2028 January or by 2028 March, 307 stations would be completed, and there will be excellent science data will be coming out from it, and we do not have enough astronomers to work on them, the data which is coming out. So places like universities, institutions have to come together and build a complete set of new young generation astronomers to be able to use this data. So that's what I think in a nutshell. I hope I have answered your questions, Kagli.
Okay. What about, are we also involved in the South African project also?
Yeah, both of them. Both of them. We are involved in all the three of them. I went to Australia and I spoke more of it. The way the telescope design is made is that the telescope manager works both for SKA.Lo and SKA.Emit. Similarly, some of the digitizers and some of the signal processing boards which are made in Italy and programmed at the Raman Research Institute and NCRA, they are useful for both the SKA.Emit and SKA.Lo. Because I went to Australia and I'm a low frequency astronomer, I concentrated all of it on SKA.Lo. But maybe by next year, as I said, when I go to South Africa and visit as a member, I would be able to tell you about SKA.Emit equally in detail. Otherwise, SKA.Lo is where my heart is, in a sense.
No, these two telescopes, are they connected or they work independently?
No. They're not connected. There are three different locations. That is SKA.Lo, SKA.Emit, and Manchester is the headquarters. And there will be data processing centers spread all over the world to collect data from both of them.
Now, what I meant was they'll not be looking at the same object at the same time and gathering.
That can happen later if there is a burst in the sky called FRBs, faint radio bursts, and if they want to look at it over a large frequency range, they may do coordinated observing. That's not at all impossible. But whether they would be looking at the same source at what time, will they do it together or will they do one after another? These are all matters which are matters of detail. But it's definitely possible. For example, simultaneous observations are possible between GMRT and X-ray telescope Chandra, UV telescopes, AstroSat. That is also a space telescope which India has built, and we should be proud of it. There are lots of simultaneous observations between different wavelength telescopes. Similarly, SKA.Mid and Lo can happen, but they are in two different regions of the sky. So how much there will be concurrent observations is a bit difficult detail, which I don't exactly recollect now, but it's possible to do it. But the telescopes are not physically connected.
Yeah, I know. Okay. How about the frequency ranges? You said they are working in particular frequency range. How is that selected? Can you give us some idea why this frequency range is
okay, one second. Let me just open it up.
Some 50 megahertz to whatever.
Yeah.
Frequency range.
Sure. Just 1 minute. Let me just go back and open the slide so that I don't make a mistake.
I'm curious about it.
Oh, sure. Most welcome.
Why this range?
Well, so this is 50 to 350 megahertz. This is the reason why for the Australia Lo, this frequency range is chosen is 1 second. If I can get that picture. I just skipped. I didn't show you this picture in complete detail. All right. This is the real picture of the Big Bang happening and the first stars which are formed around 400 million years. These are all nothing but the hydrogen atoms in the nascent state surrounding the first stars or the first galaxies. They emit radiation at 1.4 gigahertz. But these radiations or these stars are so far away from us, by the time they travel through in these regions and reach us, they get redshifted or they get weakened or they become stretched and they appear in the frequency range 50 to 300 megahertz. So that's why to really explore the neutral hydrogen atoms and the environments of stars, the firstborn stars, firstborn galaxies, the hydrogen atoms around them, the the frequency of 50 to 350 megahertz is chosen.
Oh, yeah.
And if you ask me why the mid has now chosen the other frequency range, well, you will see that when you go to much higher frequencies, the atmosphere itself starts playing very tricky things to calibrate them and to be able to see. And therefore, you will find the 190, 350 megahertz to 15 gigahertz is a kind of a comfortable range for a large telescope of this size to build. And there are many interesting science that can be done at these frequencies.
Okay, thank you.
And beyond 115.4 gigahertz, there is already the world's most famous telescope called ALMA, which is Atacama Large Millimeter Wave Telescope, situated in Chile. And therefore, the frequency range between 50 to the millimeter waves will be taken care by SKA-Low, SKA-Mid, and ALMA. It will cover the entire, more or less the entire gamut of radio astronomy that one needs to do.
I was just looking at the countries that are participating. I noticed that US and Canada, they are not there. Are they there or not?
Canada is there, but US is not there as a participating country because, no, it's not very strange. The very large array, which I showed you, just a minute, I'll just open up that part just to show you that, nothing else. Is that clear? No, this is GMRT. Okay, fine. This is the one. The very large array, okay, this very large array has undergone a tremendous amount of modification. They have Jansky VLA, which is an upgraded version of VLA. They have already produced, or they are talking about NGVLA, which is a new generation VLA, which is almost competing with the SKA on its own. And there, the view that the SKA technology is not yet fructified, therefore we should go step by step. And therefore, they decided at some stage not to join the SKA consortium, but they are going on their own. But see, the radio astronomers and astronomers are very happily a very friendly lot. They exchange ideas, they mix, they talk to each other and exchange a lot of ideas. You will find this is the Science and Engineering Advisory Committee, and he's from VLA New Mexico Socorro, and there are a number of people here. I can just go a little bit deeper and then talk to you about. They're all experts from VLA who come and participate in the Science and Engineering Advisory Committee. And the two telescopes, or the telescopes which are being built in future in America, and the one in these two countries, they talk to each other. They will share as much of information and the technology as required.
Thank you.
Murthy sir.
Uday, just one question. In the slides where you were showing, you mentioned somewhere about the collection area, 400 square meters.
Square meters, yes. Yeah.
What exactly is that? I didn't understand. How do you measure it? Is it in the sky or at what height?
No. This is
when you say 400 square kilometers. What exactly?
Not square kilometers. Sorry, sir. This is 1 square kilometer. I said square meters. If I by chance said it as 1 second, I'll show you the slide which you're talking about. I know exactly which slide you're talking about. So just give me a minute to go there. SKA numbers is what it is. Here it is. So this is 419,000 square meters.
Yep.
So this is the collecting area of 131,000 log periodic antennas. You saw that there are, where are they? Where is the nearest picture that I can show you? Oh no, unfortunately, nothing is here. No, it must be there in the next picture. 1 second, I'll just show you. Yeah, this itself. This is the kind of a dipole that we have there. And we have 256 dipoles arranged as a dish of 40 meters in diameter. And there are 512 such dishes. And the product of 512 into 256 is what gives you the equivalent number that I was talking to you about. That is 131,000 log periodic dipoles. It is the effective collecting area of these dipoles or antennas, which is 420 square meters, not square kilometers.
No, the distance between antenna stations, as in this slide, itself is 74 kilometer.
Yeah.
Why is that the collecting area is lesser? I thought
because
mathematically it would be much bigger.
No. The collecting, well, you have a very beautiful question. The man who won the Nobel Prize for this aperture synthesis, he showed that if you have an array like this, okay, this distance is about 36 kilometers, okay, this will act as a radio telescope with 36 kilometer diameter, whereas you cannot cheat the sky unless you have a bucket collecting the radiation coming from it. It won't contribute to the collecting area. Then you may ask what this contributes to. This contributes to the resolution. So the aperture synthesis is a methodology. I didn't want to go into details. It's like an interferometer. No, perfect. Your question is good. I did not go into the details of interferometer. We don't need to. You have not asked that question. So this is collecting area is this has got, let's say, for example, 25 meter antennas. If you look at it, 25 meter antennas, if you just take pi d squared by 4, call pi by 4 as equal to 1, this is 25 into 25, which is approximately 625 square meters into 30. So 30 times the 625 square meter would be the effective collecting area of the entire array. Whereas it will give you a resolution as though a 36 kilometer dish is present. That is the beauty of aperture synthesis.
Got it.
Thank you for bringing
up
one
more common man question.
Oh, no, please carry on.
If a similar telescope is being set up in, let's say, other part of the world, South Africa or somewhere else.
Yeah, which is being done.
I was just thinking if the second antenna is in the other part of the Earth's hemisphere, would that be more beneficial?
Yeah, that's why South Africa and Australia are in
portion of the Earth is always dark, the other is bright. Would it make sense that you have it in the opposite sides?
Yeah, that's why South Africa and Australia were sort of politically taken up, but they are in two different regions of the Earth.
Okay, that's already considered. Okay.
Oh, yeah, it's already considered. Oh, it's very much important, very much correct.
And one last foolish question. Will this data collected from the antenna in any way throw light on, is there life in any other planet or other part of the universe?
I thought if you just looked at the video, I'm sorry, I can't show video in a slow manner and discuss it. If I had face to face, I would have played the video again. One second, just a minute.
I thought you collect only the radiation. So how will it tell whether
cradle of
there
life.
is life or not?
No, cradle of life. The extraterrestrial intelligence is a very important point. But I can tell you one thing. Earlier part of the, what's it called, extraterrestrial intelligence, ET, what you call the ET research, was based on, can we find aliens? Are aliens in this world? Are aliens visiting us tomorrow? Etc. Whereas today, the focus of this cradle of life has changed. Was there water beneath Mars? Was there life in that water? Did the bacteria come to us from, or the amoebas come to us from the shooting stars, which came and impinged on the Earth? Where did these, single-bodied, single-celled, bacteria and amoebas take birth? Or they started from the Earth, or they came from outside? This whole field is called astrobiology. We have astrophysics, we have astrochemistry, because, jocularly people say there is a lot of bars and alcohol in the universe. Because many galaxies, not all galaxies are spirals, they are bars. And there is a lot of ethyl alcohol, methyl alcohol. So the nature has provided lots of bars and alcohol. And we have astrochemistry and we have astrobiology, which is now focusing in a slightly different fashion from just discovering only the aliens. It's called cradle of life.
So far, any breakthrough in
no, there is no breakthrough in that, yes, but the attempt is always going on. There is something called There is a laboratory in Berkeley, which I visited and spent quite a lot of time with them. There is also a telescope called Allen Telescope Array in very close to Berkeley. And they're all trying to see whether we can see extraterrestrial intelligence. But there has been no concrete evidence so far. That's why they have changed their focus. Let us not worry about getting another, hey, I'm here signal, but let us ask for whether can we see life.
Okay, thank you.
Shobha ma'am.
Thank you very much, sir. Uday sir, I had listened to your lecture in my refresher course. I'm now retired.
Oh, I see. Okay.
Even today, you have the same spirit, and after listening to your talk, many ideas, many curiosities come to the students. And thank you so much, sir. I have some simple few questions for non-physicist questions, maybe,
No
because I
problem
do
at all.
not know the.
My pleasure. Please carry on.
So, sir, two questions. One, what contribution, the recent contribution from the radio telescope in exploring the universe? And
You're talking about SKA or in general?
SKA or in general also, just to know what recent finding of radio telescopes.
Oh my God, you have put me in trouble. All right. See, recently there was a very beautiful announcement by GMRT saying that scientists from Netherlands, I think, have discovered one of the world's largest radio galaxy. And the observations were made with GMRT. All right. I don't have more details. All right. But then I can tell you something very interesting that I was a part of, which I gave a talk some time back, but there are many youngsters who are working on it. See, the first stars which were born, we were talking about this one. Give me 2 minutes, if you don't mind, to give you the answer. The first stars born here, they are surrounded by neutral hydrogen, and they were observed by a telescope called EDGES, which was built by MIT, that is MIT Hashtag, and Arizona State University. And they found that there was a signal coming from the hydrogen atoms in this part of the universe.
Oh, great.
Only problem was that signal which came from there, or which they detected, was twice as strong as what the theoreticians had predicted, and also was not exactly at the same frequency. So it was shifted in frequency, its shape was different, it was too deep, it was very bright in a sense of the word. Very bright means compared to what was thought about. Therefore, when they announced it, it's very important in science that the observations are not made by only one set of astronomers, but by a different set of astronomers. So we at the Raman Research Institute were also trying to detect these hydrogen atoms around the first stars which were born. And we said we should do an experiment to either support the discovery of this group in MIT and Arizona State University, or find out that what else do we find out? So we built a very new innovative radio telescope, which was floated on water. That is the first ever radio telescope floated on water. And we conducted the experiment for several days and found that most probably the signal the MITs are talking about are nothing but a radiation coming from their own instrument. And it is not of cosmological origin. It produced a tremendous amount of I would call as interest in the entire faculty of astronomy all over the world. And both the EDGES team from Arizona and others, and the team at RRI are continuing to do observations to show that their results are more stronger. We proved with 96% confidence that the result of EDGES is wrong. But once again, don't be under the impression that we are foes. If you were there in the beginning of the talk, you found when we were just doing a scholarship and doing a gossiping, Kagli told you that in the November month, a lady called Akshata is giving a talk in the Karnataka Physics Association. Am I correct, sir? Kagli, sir?
Yes.
And she was a student at Raman Institute. She has gone to Arizona State and she is in charge of that project to do observations. She was there at RRI just last week, and then I introduced her to Kagli. So we discuss together as to what is the experiment they did and how they are doing, and we give them our points of view. They share with us their data to show that their data was wrong. So there is a bonhomie of astronomers. It is not done with any rivalry, but with an intention to seek truth, because truth is beauty after all. Thank you. Sorry for such a long answer.
Thank you very much, sir. Sir, one last question. And nowadays we have been listening about artificial intelligence. Does this AI contribute or play any role in constructing telescopes, sir?
It may not be in construction of the telescopes, but definitely in analysis, data analysis, it would play a very important role.
Okay. Thank you very much, sir. Thank you for your very, very informative talk. Thank you. Thanks a lot, sir. Thanks to the organizers also.
Panindra?
Yeah, one last question can I ask if you have time?
Said
one
two
last
are
quick
there.
question. You just showed the last slide wherein gravitational waves are included as one of the outcomes. How exactly they play a role in radio astronomy? Anyway, maybe we can discuss.
All right.
this
No,
after.
Kagli sir, it's a very important question. You saw that recently, apart from the interferometers, the optical interferometers or the laser interferometers used for detecting of the gravitational waves, there was a tremendous amount of work done by the radio astronomers all over the world, and they published very high frequency gravitational waves. I don't exactly recollect, in the millihertz region or something like that. And how they do that is, the pulsars, many of the pulsars are rotating neutrons or are binary pulsars. There is one going around the other. I told you that pulsars are neutron stars, which are very, very heavy. A 1 spoon of neutron star can weigh several tons. So the gravitational field between two binary pulsars is very high. And when two pulsars are going around each other, or it's in a binary system, you will find that they release energy in terms of gravitational waves, and the time of arrival of the pulses change with time. That means the P becomes P dot. That means the pulsar rate, the rate at which the signals are being received from the pulsars, they get decelerated. They become, they are going into the central magnetic field. So they have a P dot. There is a dP by dt. Yes. They measure dP by dt expected from an ideal orbit, or if they are losing from gravity, and they estimate how much of gravitational waves come from those deviations from the expected dP by dt. That's how they detect. That could be a very detailed talk. I don't mind. I can't give a talk. I can do it, but as a seminar. But there are friends of mine who are experts in telling you about it. There is something called IAPT, which is Indian Association for Pulsar Timing, who time these pulsars, which are known as very accurate astronomical clocks. They detect the variation in the times and tell you how much of gravitational waves could be seen in them.
Oh, thank you.
Yeah, sorry, Panindra. I apologize. Please carry on.
It's okay, sir. So I have this doubt. So within 150 megahertz to 350 megahertz or 50 megahertz to 350 megahertz, if you're observing sun, what solar physics can we get from it?
You will have to ask a solar astronomer. You're asking an extragalactic cosmologist this question.
Oh,
all right.
okay.
The simplest answer is they get a lot of information about coronal mass ejection. There is a lot of information which has come to them about different types of solar bursts.
Okay, sir.
You can read papers related to MWA. There is a Murchison Wide Field Array in which RRI was involved in building in the early stages, and there are lots of papers on what solar astronomy can be done with that SKA, with MWA, sorry, with Murchison Wide Field Array, and therefore extend it to what can be done with SKA.
Okay, sir. So I was actually in this RRI in Gauribindur Observatory. There is one interferometer recently built last year. So I'm using that to record the data of the sun between 150 to 350 megahertz. So that's why I wanted to ask what I
Oh,
can
sure,
do, what
you're
physics I
most
can do in
welcome. I
that.
mean, if you're working with, whom are you working with at RRI?
Prabhu sir,
Prabhu sir, but Prabhu may not be an expert in solar astronomy, but he will definitely be a very good expert in detecting the kind of signals that you have got from there. He's using AI to detect signals. He may
Yes,
be
sir. That's also one of my
detecting.
project, like using machine learning to detect.
So here it is, Shobha, an answer to your question. He is using machine learning to detect solar bursts.
Solar flares.
Solar flares, which can affect the space weather, which can affect our communication, which can affect our satellite communication. A very, very sensitive, very important piece of information from radio astronomy.
Yes,
correct?
sir. Yes, sir. Yeah, thank you for that. Thank you for telling about the MWA.
Yeah, when I come to RRI, we can talk about it and I can show you all those papers. I'm not an expert in that field, but I know the field. I can talk to you about it.
Okay, sir. Yeah, thank you, sir.
Radha Krishnan, sir.
Yeah, Dr. Udeshankar, amazing presentation, amazing things to learn as well. And I just learned that it's not just astrophysics, astrochemistry, astrobiology is also going to happen. So being a chemist, I am also feeling part of the whole thing now.
Oh, wonderful, yes.
My question is, in one of the videos, there's a mention of what is the purpose of all these studies. The lady responds, it is for education and development. How this development part is understood and how it is connected to development of nation, development of people. Can you throw some light on this, Doctor?
Oh, yeah, because this is a very huge project. You just now heard that one of the young man, Panindra, is doing some observations in Gauribindur and using artificial intelligence and deep learning to really look at the solar bursts. So the science and technology that people are doing, astronomy has always played a very important role in science and technology. Like my own younger colleagues from Raman Institute, I've left, I'm retired now. They are into, for example, developing a probe on the other side of the moon to detect signals from the first stars which were born. Therefore, they're building technology which can go to the other side of the moon, because the other side of the moon is the only place where there is no man-made interference. You don't see the emission from Earth, and therefore that is a very safe zone to conduct experiments. And the astronomers from India, enthused by all these things which are going on, have made a proposal, and that has been sort of in discussions and seen a very good progress amongst the space science, the ISRO and RRI, in a sense of the word. And a large number of students and industries are working in it. SKA itself, in terms of the nation building, has a lot of, $1 million of contracts have been given to industries. And therefore, industries will also have a very good say in the kind of technology they develop, and they will get in new technology from other countries. For example, the signal processing board was designed in Italy. It has come to RRI for, I'm sorry, I'm using RRI because that's what I'm well knowing about. I understand about it. So that's coming for the software development. And so many of our students who have worked in RRI, my God, they have gone to all over the world. Wherever I go, I went to Australia. I met so many of my students there working in different radio telescopes, different factory environments, different industries. And therefore, we really have a very good contribution to technology and science from the students who come to us to do astronomy. And the nation building is in terms of industry. That's what I would say it as.
Thank you, Udeshankar.
For example, I didn't show, let me just see whether we have I'm always a man of arrays. This is a Gauribidnur T array, which is what Panindra was telling you about. This is 1 kilometer by half a kilometer array in Gauribidnur, which consists of about 1,000 dipoles. We were talking about SKA, which is 131,000 dipoles. This is a very preliminary or a primitive telescope in which I did my PhD, And for SKA, with Govind Swarup, that's why I'm very proud of Govind Swarup. I worked with him for more than around a decade in the last phase of his life. This is the low-cost 12-meter prototype for SKA, which was built at Raman Research Institute. So the entire, design of this, which was there already with Govind Swarup, but he brought up the design, but there was no real structural analysis, structural measurement, nothing was there. But we took the telescope design from a paper design to a working radio telescope, and we demonstrated how much it costs, up to what frequencies can it go, and things like that. And this was completely built at RRI and installed in Gauribidnur. It's still there in Gauribidnur, though it's not extensively used for astronomy. And many of the parts of this telescope, look at the supporting structure, the motor control, the gears, the supporting, the hub, as we call it, all were made by local industry in Bangalore. Imagine if we had successfully demonstrated that this goes to very high frequencies, then India would have made a large number of such dishes.
Can I ask you one more question?
Oh, please, please.
Okay. You mentioned about this dark matter, dark energy, and dark matter is about 20, 22, 23.
About 23%, yes.
What it could be? Any?
Oh, there are lots of candidates, but nobody knows what the dark matter is made up of. And dark energy, particularly, which is a new sort of a not a very new concept, but which is sort of the WMAP showed it with definitism. We all know that due to the Big Bang, the universe is expanding, but 2 years back or 3 years back, I don't exactly recollect the time, astronomers won Nobel Prize for showing that the expansion of the universe is accelerating. So we are not only in an expanding universe, we are in an accelerating universe. And they said that is due to the dark energy, which is in addition to gravity, which is pushing them out. Actually, gravity should have been pulling them together. Whereas this is an accelerating universe. Expansion means the objects are made to go away from each other at a faster rate. And this, they say, as, dark energy. So where does it come about? How exactly this manifests? They're all things which we may have to wait for SKA to tell us, or my grandchild to do her PhD or his PhD to come and give a talk to your son.
And dark matter is dark because it is not emitting any...
No. It is dark because, yes, you're right. It's not emitting any radiation, neither radio nor optical. We are only seeing it by its gravity. That's why it is called dark matter.
But how the gravity is understood?
Oh, beautiful. I had that as one of the possible slides, but I removed it later because, see, the hydrogen atoms, which I was telling you about, emit 1.4 gigahertz, which is very close to the frequency of our mobile phones, right? We work at 700 megahertz, 800 megahertz, 1.4 gigahertz, all right? So when people measured the rotational velocities of spiral galaxies, they found that the galaxy existed beyond what is seen with the eyes, and they had speeds which are much more than what could be predicted from the matter we could see. So therefore, the 21 centimeter hydrogen gave what we call as rotation curves of our galaxies, and the rotation curves of galaxies indicated what could be the mass inside, but all the radiation that we could see from them could not account for that much of mass there, and we called it as dark matter.
Oh.
That's how the dark matter was discovered, but a lot more has gone on in research. Lambda CDM, and well, they're more technical, but this is exactly what the dark matter, how dark matter was discovered.
Thank you, Doctor.
Supriya?
Sir, it's been...
Thank you very much for giving me an opportunity to interact. See, as I said, I might have had a less number of audience, but they were all so interested, so active.
Yes.
They asked me questions to make me think and answer them. So thanks a lot to all the audience who
Sir,
participated so actively.
Yes, sir. Thank you very much, sir, for your time and your insights. It's really very interesting and new for us, new topic for us. Thank you. We follow you for more information. Thank you.
Sure, most welcome.
Thank you, Anandar, for being with us.